And kittens. Yes, I have watched it. I wanted to make a YouTube video because the last PowerPoint I did not do a little voiceover, and I want to clarify some stuff for you as well as kind of put together what you guys have been doing for the past week into one sort of nice package. I hope you all are doing well during these trying times. I appreciate all of your messages about my grandmother. I really do. But, we still have some work to do. So today, we're going to, like I said, sort of culminate and review everything you guys have done for the past week. So by the end of this lesson, you should be able to write and balance nuclear decay equations using some new reference tables that we haven't talked about yet. Before we get to this, I kind of want to review something with you guys that you may have noticed during the POGL activity that you just finished up. And that is that there are two different types of nuclear equations. One we call a natural transmutation, and one we call an artificial. So I'll put them both up here, and you'll see the main difference. If I were in class, a lot of you guys would shoot your hands up right now. On the one on the left, we only have one nuclear reactant. The one on the right, we have two or more. So you can see on the left, we only have uranium on the left. But for the right equation, we have aluminum and helium. Now, the natural transmutation happens on its own. Remember that spontaneous means that we don't need to do anything. It will happen by itself. So uranium-235 will break down into thallium and helium. You don't have to do anything. However, the one on the right has to be forced. So you have aluminum and helium colliding together to make phosphorus and a neutron. You need to put those two things together with enough energy to have it happen. So again, natural transmutation, you only have one nuclear reactant. Artificial, you have two, and you have to force it to happen. So let's say I gave you this question. Which nuclear equation represents a natural transmutation? Well, again, natural transmutation only means one reactant. So we look for the one with one reactant. Uranium-235 going to thallium and helium. All the other ones have two things on your left side. So an artificial transmutation is something that's induced or forced, caused by the hitting of nucleuses with particles or other small nuclei. I'm going to go over this stuff tomorrow. There's two different types of artificial transmutations that you guys are going to know. But for now, I just want you to be able to distinguish between natural and artificial. So as you guys saw in the video, in the POGL, in the notes, things break down. So we can write how radioactive elements or radioactive isotopes break down using a very specific method. So we're going to need three things to help us out. Table N tells you the particle that's emitted. Table O tells you what that particle is. So table N, let's say you have calcium-37. Table N would tell you that calcium-37 releases a positron, but table O will tell you what a positron is. So if you don't know a certain term on table N, you just go to table O. And then, of course, the good old periodic table. So the main thing to know is that we need these three tools, as well as we need to make sure the mass and charge are balanced. You guys sort of did this in the POGL. I'm going to go over it a little bit more in depth in this lesson. But you have to make sure that your sides are balanced. Just like when we're balancing equations, we have to make sure these two things are the same on both sides. Now, what I'm going to put a note here is that steps 1 and 2 are only for natural transmutations. So you'll see in the worksheet that you guys do that if you have an artificial transmutation, this process of writing the decay equation is so much easier. Natural, there's a couple extra steps involving table N and table O. So let's say I gave you this problem. Please write the natural transmutation of calcium-37. There are different tools/steps that we can do. I'm going to go through these one by one, but first we have to write the parent nuclei. All that means is calcium-37. We write out calcium-37, but where did I get this 20 from? Why is there 20 there? Well, if you remember back to PowerPoint 1, this bottom left number represents the atomic number of the element, which we grab directly from the periodic table. So if we go to the periodic table, calcium, its atomic number is 20. Remember, that goes on the bottom left, and the 37 is the number of protons and neutrons, or the atomic mass. So we wrote the parent nucleotide. Step 1 is done. Now we need to go on to step 2, which is find out how calcium-37 breaks down. So if we go to table N, we have to find calcium-37. I'll give you guys a second to find it. It shouldn't be too hard. It is the third one down. So we can see that the decay mode of calcium-37 is this B positive. So we just went to table N, saw that calcium-37, the nucleide, breaks down by B positive. So now we have this information. We have calcium-37, and it breaks down with B positive. But what does that mean? What is a B positive particle? That's where table O helps us. So table O is going to help us get from here to the notation of what a B positive particle is. And if we look, table O gives us all of our different symbols: alpha, beta, gamma, neutron, proton, positron. We're just looking for that B positive, which is right here. Now, one key thing. See how there's this He42 or alpha42? You can write either one. It doesn't matter. So here you can either write it using an E or a beta symbol. Here you can either write the E or the positron symbol. Doesn't matter. So now we have a little bit more information, right? We know the parent nucleide. We know the decay mode. We know what that particle is. And now we have to make sure that mass and charge are conserved. So let me explain what I mean by that. Mass and charge must be equal on both sides. So if I gave you this, we have polonium-218 going to helium and X. We need the mass and the charge on the left side of the equation to be equal to the mass and charge on the right side. So if I draw a little line here, we can think of it like the left side and the right side. They need to be equal. And you did this in the POGL. So if you notice, we can think of it like this. Our top number on the left is 218, which means we need our right side to be equal to 218. Well, the 4 we get from the helium plus X, well, what's our top number going to be? Our top number is going to be 214, because 4 plus 214 equals 218. Pretty simple. What about the bottom number? Let's see if I could change the color. Yes, I can. So the bottom number, 84, right? Same thing. We need that to be equal to the sum of our bottom numbers. In this case, it'll be 82. So if we were to fill in X, X is 82 and 214. That's step 1. However, X is not an element. If you look on the periodic table, X is not an element. So we can't leave it as this X. We need to change it to its elemental symbol. And if you look on the periodic table, remember that we can tell what an element is by this bottom number, by the atomic number. So if you look, 82 relates to PB. So the missing piece in this is just PB214, and we write that 82 because that's the atomic number. So in this scenario, right, we need to conserve our mass and charge. So we're going to add something which is going to help us conserve the mass and charge. Well, what is our numerators? Well, we have 37 on the left and 0 on the right, which means our numerator has to be 37. And we have 20 on the left and 1 on the right, which means our denominator, well, I'm saying numerator denominator, but it's really top number, bottom number, right? Don't think of it like a fraction. Sorry about that. But our bottom number, or atomic number, has to be 19, because 19 plus 1 gets you 20. And if we look on the periodic table, right, step 5, the thing with an atomic number of 19 is potassium. So that is your natural transmutation of calcium-37. We have the parent nuclei, we figure out the decay mode using table N, we write in the particle that's given off using table O. In this case, it was a positron. And then we conserve the mass and charge, which is just really the top numbers and bottom numbers. And we make sure to put in what that element is. We don't just leave it as an unknown. We put in the symbol. Let's go through 3 more. So Pu-239. We're going to start off by looking at what Pu-239 is and how it breaks down. And if you go onto table N, you will see that Pu-239 actually breaks down via alpha decay, and an alpha particle is He4 2. Again, this 94, all I did was go to the periodic table, go to the symbol for Pu, and see that its atomic number is 94. Now it's steps 4 and 5. We have to conserve the mass and charge. So we have 239 on the left, 4 on the right. So that means our numerator will be 235, or sorry, top number will be 235. We have 94 on the bottom on the left and 2 on the right, which means our bottom number will be 92. And again, if we go to the periodic table and we look for the thing with the atomic number of 92, you'll see that it's uranium. Nice and simple. Iodine 131, again, go to table N, see what iodine 131 breaks down via. It breaks down via beta decay, okay, which means we have iodine on the left, again, the 53 is the atomic number, breaking down to E0 negative 1, and we have to find out the missing pieces. Well, the top number is easy because it's just going to be 131. The bottom number, be careful, because this is a negative. Instead of these numbers still have to add to get to 53, right? So which means this number, stick with me, has to be 54, because 54 plus a negative 1 will get you 53. And if we look, the thing with an atomic number of 54 is Xe, xenon. Ooh, that's a baddie. And lastly, cobalt 60. I'm telling you, it breaks down via gamma, and gamma is easy because if you remember, gamma is just energy. There's no mass, there's no charge. So in this case, our top number is going to be the same as the left, and our bottom number is going to be the same as the left, which means that the thing with an atomic number of 27 is cobalt. So cobalt 60, when it decays or when it breaks down, is literally just going to give off this energy. And remember, gamma is dangerous because it has the most penetrating power. It will penetrate concrete or your body or something else and mess it up because it's so high energy. So these are relatively simple. I just kind of wanted to walk you guys through it in case you're having trouble with it on the POGL. The worksheet that I posted that goes along with this PowerPoint will just have you sort of doing this, right? Breaking down the molecules, talking about their decay mode, and then the bottom half, you have to just finish the equation. So you're just going to have to conserve mass and charge and say if it's artificial or natural, which remember just relates to how many nuclear reactants there are. So try out that worksheet. Let me know if you have any questions. And finally, stay safe, stay healthy. Let me know if you guys need anything. Thank you.